Hey everyone, welcome to this tutorial series / crash course on ROS2. If you have never used robot operating system before, even ROS1, or if you want a practical and quick refresher of the basics, this series is for you. And very quickly, so you don't get confused, ROS means Robot Operating System, ROS1 is the first version of ROS, and ROS2 is the second version of ROS. ROS2 is now stable enough to be used, so this is the recommended way to start with ROS. In this series, I will sometimes use the term ROS or ROS2, and when I do, I will be talking about the same thing. So the goal of this crash course is simply to get you started with ROS2 in a very short amount of time. You will learn how to install and set up everything, how to use the main ROS2 concepts with the command line interface and tools, and you will also write your own ROS2 programs with Python. In fact, throughout the series, we will do together a small but complete ROS2 application using a 2D simulation of a robot. I have designed the series so that you can really get a better understanding of the global picture and also get some practical knowledge that will be useful for your next steps with ROS2. In this tutorial series, I will target the ROS2 Humble distribution, but the concepts and most of the code will also work for other ROS2 distributions. Now, there are some prerequisites you need in order to use ROS. Basically, you have to be familiar with Ubuntu and the Linux command line, and to write ROS code, you will also need to know a bit of Python and C++. But here we will stick to Python, so just Python will be fine. Now, this crash course is great to get you started, and if you want to go further and dive into more details, concepts, projects, and C++ code, I have also a much bigger and complete course on ROS2. So if you are interested, I've put a link in the video description below, and I will talk a bit more about this later on. Now let's get started with the series. In this first episode, we are going to install and set up ROS2 Humble on Ubuntu 22.04 so that in the next episode you can start using ROS functionalities. Here I am going to start from Ubuntu 22.04 that I have already installed on a virtual machine in VirtualBox. You can use either Ubuntu installed with a dual boot on your computer or in a virtual machine, it's up to you. So to install ROS2, let's first open a terminal, and I'm going to put this on the side, and let's also open a web browser. I'm going to open Firefox here. Okay, and let's also put this on this side, and let's search for ROS2 Humble. Okay, you will get to, so let's zoom a bit here. You will get to this page on docs.ros.org. Okay, make sure you have Humble in the URL. If you don't have, maybe you are reading the documentation for another version, so let's click on Humble here. And then here you can see the table of contents, and you're gonna choose Installation and click on Install Humble. All right, now you're gonna choose the binary packages installation, not building from source, and you're gonna go here with Ubuntu and Debian packages. And now we have the instructions to install ROS2 on Ubuntu. So I'm gonna follow here just the instructions that we need. And just a quick note is that maybe when you browse this documentation, the instructions will have changed a tiny bit, but that's okay. It's just because, well, the documentation is quite frequently updated. So if you see something that is just a little bit different, no worries, just follow the instructions and everything will be okay. So the first thing is we need to make sure that we have UTF-8. So we're gonna type locale in the terminal here and make sure that we have UTF-8. So here it's good. If you don't have it, then you're gonna, well, just run those commands, put your passwords. Okay, so that's gonna install some stuff. It's already installed for me. You run those lines here. Actually, let's put this like that. All right, so you run the 4 lines. And then let's check local again, and of course it's okay, you have UTF-8. Now you will need to set up the sources, because you can't just install ROS2 like that. You will need to set up the sources so that your computer here can find where to download ROS2. And well, those instructions here may be removed in the future or maybe modified. So if you don't see that, don't worry and just go to the next step. But what you can do is just do this apt cache policy grep universe And if you see stuff like that with 500, and then, well, you see Jammy and Universe stuff, then that's okay. You don't necessarily have to have the exact same thing with, for example, US here. You can see I have FR, but the important thing is that you see 500 and Universe. So if you don't have those, you can run those two commands here. I'm not gonna run those, but you can run them if you don't have the correct lines. And now is really the step to actually set up the sources. So you're gonna run this line first to install curl and different functionalities. So here actually I already installed it before, so nothing to do for me. Then you run this line, okay, and add the repository to the sources. So you just copy and paste the line, and then you are good. What you can do is now do an update, so sudo apt update. This is going to update, and you can see that you should have something like that, packages.ros.org with ROS2. So you will have something similar. And one important thing is that before you install ROS2, let's do sudo apt upgrade to upgrade all the packages we have. Okay, so you may have a lot or not, it depends. When was the last time you actually upgraded your system? So I'm just gonna put yes and wait for the upgrade. Okay, and now you can go down into the instructions. So you have a warning here, but nothing to worry about if you have correctly updated and upgraded the packages. So now everything is up to date on the system. Now you can install ROS2. So here you have two choices. You can install ROS2 with this ROS-Humble-Desktop or ROS-Humble-ROS-Base. So ROS base is actually, so you can see the bare bones, just the communication, the command line tools. You don't have any graphical tools and utilities. This is what you would want to have in a limited system, for example, on a Raspberry Pi, or if you have a computer with very low resources, or if you don't have a graphical interface, for example. But here what we want is to have the base plus also all the utilities, some demos, some tutorials, and some graphical tools. So we're gonna install this. So you just do sudo apt install ROS Humble Desktop, you press enter, and here, well, I've already installed it before for this tutorial, but you will see a lot of packages. So maybe you will have a few hundreds of packages for a few hundreds of megabytes to download and a few giga to be added to your hard drive. Okay, so that's gonna be a lot, so you press yes, and then you can wait for a few minutes. It's gonna depend, of course, on your internet connection speed and the performance of your computer. And right, once you have successfully installed this, then ROS2 is installed. And just a quick note here is that if you want to install any ROS2 package in the future, well, this is very simple, because all the ROS2 package for the Humble distribution, for example, will be ROS-Humble-something. So you will just need to run this command, sudo apt install ROS Humble dash the name of the package. So this is quite easy. Now, well, ROS is installed, but we can't just use it like this. We need to set up the environment. Okay, because, so let's clear this. If I just do ROS2, you will see that ROS2 command not found. So to be able to run ROS2, first you need to install it, which is done, and then you need to source a setup script here in every session or every terminal where you want to use ROS2. And so if we go to /opt, you will see that this is where ROS is installed. You can go to opt/ROS, and then you will see Humble. This is the distribution we just installed. So ROS Humble is actually ROS2 Humble, okay? And here you see we have a setup.bash script. And this is the script that we need to source here, okay? We need to source that. So let's go back to home directory and let's just source this script. And now that this is sourced, look at that. If I do ROS2, now, so we have the help actually of the command. We don't have ROS2 command not found, we have the help of the command, okay? Which means that this has been found and ROS2 is correctly installed and set up. Now the thing is, let's say I open new terminal and I do ROS2. Once again, I have the same problem. So I need to set up the environment. and now it works. Okay, so I will need to set up the environment for each terminal I use. Or if you connect with SSH, for example, you will need to set up the environment for each SSH session. And so that's not really convenient. All right, so what we're going to do instead is we're going to add this line to the bash rc file in our profile here for the user, so that this line is going to be executed every time we open a new terminal or session. Okay, so to do that, we are going to use gedit, and then you can do bash rc. So tilde to go to your home directory /.bash rc. So this is a hidden file. Press enter, and you can see we have already a lot of lines, and all this stuff is going to be executed when you open a new session or a new terminal. So you go to the very end of the file, and let's add a new line here. And what do we put? We put just this one. Okay, source /opt/ros/humble/setup.bash. Let's save the file. Let's quit. And now let's just quit all the terminals that we have. Let's open a new terminal. And when you open the terminal, this line will be executed because it's in the bash rc. Now I can do ROS2, and you can see now it is working. So when you have ROS2 with usage ROS2 and the help of the command, it means that ROS2 is correctly installed and configured. And congratulations, you are now ready to start using ROS2. In the previous tutorial, you have installed and set up ROS2. Now we are going to directly start a ROS2 node and understand what it is. And very basically put, a ROS2 node is simply a ROS2 program that's going to interact with ROS2 communications and tools. Okay, so I have 4 terminals here, and let's start a node. So where can we find a ROS2 node? Well, actually, when you install the ROS2, there are some packages that are actually example packages that you can use directly to start a node without having to create one. So we're gonna run ROS2, okay, so the ROS2 command line, and then space run. And after this, you will need to provide the name of a package. So the ROS2 nodes are gonna be organized in packages. Okay, for example, you have a package for a camera driver, a package for a navigation of a robot, etc. In each package, you can have different programs or nodes. So here, the package we want is called demo_nodes, and you can press tab here, and you can see we have auto-completion. So if I press tab twice, I get this auto-completion, and I have several choices. I'm going to choose demo nodes cpp, and then I press space again, and now I need to provide the name of the node. We're going to go with a node that's name is talker. So ROS2 run demo node cpp talker. Then you are going to press enter, and you can see we have something. So the node is running, so that's a program that's running, and you can see it is printing stuff. Now you can press Ctrl+C to kill the node. And just one quick note is that if you don't have this, but if you have ROS2 command not found, it's because you have not correctly set up the environment after installing ROS2. So in this case, make sure, let's do gedit bash rc. So let's go to the bash rc file. Let's go to the bottom, and at the bottom you should have this line, okay? Source opt ROS Humble setup.bash. And now let's come back to the node. So what you see here on the screen are logs from the node, and this node is named talker. Here you can see the timestamp, and this is what's coming from the node. So that's simply a program that's gonna print publishing hello world with a counter. So let's run this node again. Now we have running node. Now in this terminal, let's do clear, and let's do ROS2 run demo nodes cpp. So I'm going to use the same package, and in this package we have other nodes. For example, we have listener. So listener, okay, like that. I can press enter, and look what's here. I heard hello world 22, and that's exactly what is written here. Okay, so I have one node here, one node here. Let's do rqt graph in another terminal. So what is rqt graph? RQT graph is a tool. This is a ROS tool that you can use to actually see the graph. So what is the graph? Let's run it, and okay, let's put it full screen and let's do refresh here. So what is the graph? The graph is simply the representation of all the nodes that are running. And so you can see that here we have one node called talker, which is the first node we have started, and one node called listener, which is the second node we have started. And this is actually a topic, so we are going to come back to topic later in this crash course. But what you can see here is that this node is talking to that node. So the node here, talker, is sending some information to the node listener. And that's what we can see here. You can see that what's being sent here is received by this program. Okay, let's say I kill the talker node. Okay, you can see the listener node, I press enter here, is still working, is still waiting for stuff to receive. When I start again, you can see publishing hello 1, 2, let's kill it. And you can see here, I heard hello world 1, 2, and 3. So with this example here, you can see that a node, well, is simply a program that you're gonna run. So it can be any program. It can be a C++ program, a Python program. And the specificity of that program is that it's connected to the ROS2 environment. So in this case, the node here named talker is gonna send some messages using ROS2 communications. And this node named listener is gonna receive messages also using ROS2 communications. You can note also that the logs here are handled by ROS. So nodes are also using tools like logging, and also when we launched the RQT graph, which is a visual tool, you can also debug the nodes. So a node, well, basically it's a program that's gonna use ROS2 functionalities. Now let's stop everything. So let's do clear and let's stop the RQT graph too. Okay, let's clear this and let's also stop with Ctrl+C and clear. So now we have nothing running. So actually, if I do RQT graph, you can see, so I can refresh here. Well, we have nothing because there is no node currently running. I'm going to use a second example. We are going to run, so ROS2 run, so that's the same command. Now we are going to go in the turtle sim package. So turtle sim is a great package to start experimenting with robots in 2 dimensions. And so from turtle sim, we're gonna go with turtle sim underscore node. Okay, so name of the package turtle sim, name of the node, turtle sim node. I press enter. And what do we have? Oh, you can see we have a window, so graphical window, that's blue, and inside we have a turtle. If I go back to RQT graph, let's refresh. You can see we have a node called turtle sim. That's the node we have studied here. And this node, well, the previous nodes we have studied were just nodes that were interacting with the terminal, sending logs and messages. Here you can see this node is also creating a graphical interface. Now let's start. So I'm gonna actually make it here, so change the layout a bit and keep the turtle here. In this terminal, let's do ROS2 run turtle sim, so still in turtle sim package. We're gonna do turtle underscore teleop key. So I press tab here and let's press enter. This node here is going to listen to what you type on the keyboard. You can see here reading from keyboard. So this is going to listen to what you type, and then let's see what it's gonna do. So for example, I'm gonna use the arrows of the keyboard. So the up arrow, and you can see that the turtle here has moved. If I use the left, okay, it's turning up, down, right. You can see I can make the turtle navigate, okay? And so what's happening here? Well, we have one node here that's responsible for creating a graphical interface with a turtle. And then we have one node here, so that's another program that's responsible for reading from the keyboard. And then, as we can guess, sending some command to that other node. Okay, so this one will be sending commands. This one will be receiving and executing the commands. Now, if we go back to the RQT graph, let's refresh. And let's keep the nodes only here. You can see now, so we have 2 nodes. We have the turtle sim node and the teleop turtle node. So we have two programs running on the ROS graph. And well, we have different communications here, but you can see there is one going from the teleop turtle to the turtle sim. This is the turtle1 command velocity. That's the topic, and again, we're gonna see topics later in the course. But you can see basically what's happening. This program is gonna send commands to that program. All right, and that's exactly what's happening. And make sure, okay, that when you want to make the turtle move, you have to actually select this terminal with the turtle teleop key, okay? So that when you use the keyboard, you can see the turtle is moving. If you select another terminal, well, you're not gonna be able to move the turtle. You have to select that one. All right, and that's pretty much it for now. So what is a node? Well, a node is basically any program that also has access to ROS functionalities and ROS communications. We have seen that with nodes that just communicate between each other and that print logs on the terminal. You can also have nodes that create graphical interface, nodes that interact with the hardware, nodes that also, for example, host a web server or call a web server, well, anything. And now congratulations, because you've already seen a lot of things with ROS2 nodes, also with the command line, so you have an introduction to command line, and some ROS tools like RQTgraph. From the next tutorial, we are going to see how to create your own ROS2 nodes, so you can create your own custom ROS2 programs. So let's start to write some code, but actually before we even write code, we need to do a bit of organization because we need to create a ROS2 workspace. You are not going to create your code wherever, okay? We need a bit of organization. So you are going to create a ROS2 workspace. In this ROS2 workspace, you will organize your code through different packages, and you will also be able to build and install your custom code in your workspace so that you can actually use it. Also, if you work with a team, for example, and if you need to share code, well, that's what you are going to share. You are going to share a specific ROS2 workspace with many nodes inside, so you can easily collaborate. All right, so the first thing we are going to do is we are going to install the build tool for ROS2. Because as I told you, this ROS2 workspace, you're gonna write code, but you're also gonna build your code and build your ROS2 nodes. And what is the build tool for ROS2? The build tool is named Colcon. So let's just install that. Sudo apt, so we can do sudo apt update maybe, put the password. Okay, and then we can do sudo apt install. That's gonna be Python 3 -colcon -common extensions. So just like that, and you can use the auto-completion as well. So let's press enter. Okay, and let's just install that. So yes, and let's wait a bit. Okay, great, and now it's as simple as this. Colcon is installed and we can use it. There is just one more thing I'm gonna show you now, is because if you just use Colcon like this, so that's going to be a command line tool, you will not be able to use the auto-completion for the different options of the command line. So we need to do something more to enable that. So let's do clear here, and let's go to cd/user, so usr share, and then Colcon, so Colcon _ arg complete, so you should have this now, and then /hook. And in here you can see we have a bash script. And that's going to be very similar to what we did with the environment setup for ROS2. We're going to need to source this bash script so that we can use the auto-completion for Colcon arguments. And instead of sourcing this script every time we open a new terminal, I am simply going to do gedit here bash rc. So let's open this. And let's put that on the side. All right. We are going to do source. So after the line to source the ROS2 installation, I'm going to add another line source with this, so the path here, right there, /user /share /colcon complete /hook this script right there. Okay, so we can make sure that this is gonna be sourced every time we open a terminal or a session. Let's save the bash RC and quit. Okay. Now let's go back to our home directory. And here either you open new terminals or you can just do source bash RC. So you can make sure that the changes have been made. And let's also source every terminal we have for now. Source, so dot bash rc here and source dot bash rc. Okay, so Colcon is installed and we can also use auto-completion in all terminals that we have, plus any new terminal that we open will be already correctly configured. Great, now we have Colcon and the auto-completion. Let's go back to creating our workspace. And so what is a ROS2 workspace? Well, nothing more than a folder actually. So I am in my home directory. I'm just gonna do mkdir. I'm gonna name it ROS2_WS. So that name is actually quite common. That's something you're gonna see quite often as a ROS2 workspace. You can use any name you want actually, but I'm gonna keep this one for this tutorial. So I press enter and then let's go to this ROS2 workspace. So now we will need to configure this and to actually say that this is a workspace. So for now it's empty. We're going to create, so mkdir src. We're going to create a source folder that should be named exactly src, okay? So now you have a ROS2 workspace and inside src folder. So in this src, that's where you actually are going to write your ROS2 node. And how is it going to work? Well, you already have a ROS2 global installation. So you are going to be able to use the functionalities and the nodes from the ROS2 global installations and also your own custom ROS2 nodes on top of this global installation. So we can also call this workspace an overlay. Okay, that's going to be an overlay on top of your ROS2 global installation. All right, and now, well, what we can do here by going to this ROS2 workspace, not in the source, but in this ROS2 workspace directory, we can do colcon space build. You press enter and you can see, well, 0 packages finished because we have nothing in the source directory, but the build has been successful. If I do ls, you can see now we have 3 new folders. We have build, install, and log. So Colcon is going to fetch the code that is inside the source folder, and then it's going to do stuff, it's going to build, and it's going to install nodes inside the install folder. And if we go to install here, you can see that we have actually another setup.bash script. And what do we need to do? Well, we will actually need to source this setup.bash script if we want to be able to use our custom ROS2 nodes. Okay, so once again, I'm going to go back to, let's say here, gedit bash rc. And we're going to need to do, so let's say I'm here in the home directory, I can do source tilde dash ROS2 workspace install setup.bash. After I do this, I can use the nodes that I have created. And so this line, I am actually going to copy it and add it after the last line of the bash rc, right here. So now in the bash rc, I have 3 lines. 1 line to set up the global ROS2 installation in the environment, 1 line for the Colcon auto-completion, and 1 line for the custom ROS2 workspace that we have created. So now I save, and either you can source the bash rc in, so actually not gedit, but you can source the bash rc in your terminal so that it's going to be able to find your custom ROS2 workspace, or you can just open new terminals. And using this ROS2 workspace, you are now ready to start creating a ROS2 application. So you now have a ROS2 workspace, which is correctly configured and where you will be able to write your code. But there is just one more thing we need to do before we can start actually to write a node. We need to create a package. So let's go to our ROS2 workspace in the source directory. We have nothing for now. And we will actually write nodes inside packages. Okay, so packages will allow us to organize the code in a better way, also better organize the dependencies between packages. So let's see how to create a package. To create a package, well, first you go to the source directory of your workspace and you do ROS2 pkg and then create. Okay, ROS2 pkg create and then the name of the package. Let's go with my_robot controller. Make sure you don't use spaces, okay? If you want to have different words, use underscores. And so why do I name the package like that? Well, we're going to control, so if you remember the turtle sim robot in 2D that we have tried before, we're going to create a package and inside we're going to write some nodes to control this turtle. So that's going to be a robot controller package. And why do I name it like this? Well, we're going to experiment with some nodes inside this package, and actually the final project of this crash course is to control a robot. So I'm just naming it controller. And I just put my robot. This is something that is quite common, is that if you create a package for a robot, you're gonna put the robot name first and then what you want to do. So for example, it can be a controller, can be a camera driver, a navigation package, etc. And if your robot is named, let's say C3PO, then you're gonna have, for example, C3PO controller. That's a good practice to have. And then each package is gonna be one subpart of your application. Okay, and the package can contain many nodes. Each node will be specific to this subpart. Okay, so here if I have a robot controller, each node will be specific to the control of the robot. If I have a camera package, each node will be specific to the camera functionality. And then, of course, between packages, you can have dependency. You can say that package A depends on package B, depends on package C, etc. So what do we have for now? ROS2 pkg create name of the package. Now we will need to specify if this is a Python package or a C++ package, okay? So either we are going to write Python nodes or C++ nodes. And for this one, I'm gonna go with Python. So you do -- build type like this, and then you're gonna need to provide ament underscore, and here I'm gonna press tab, okay, not enter, I'm gonna press tab twice. And you can see we have two choices. We have ament CMake and ament Python. We're gonna go with ament Python. So what is ament? Ament is the build system, okay? Colcorn is the build tool that we have installed, and that's gonna use the build system named ament. So ament Python for a Python package, ament CMake for a C++ package. Great, so now we have a name, we have the build type, and I'm gonna add dependencies. So -- dependencies, and the dependencies are basically other packages and functionalities that we are going to need to use in this package. And so here I'm just gonna write RCLPy, okay? What is RCLPy? We're gonna see that when we write the node actually. This is the Python library for ROS2. So because we're gonna write Python code, we need of course to use the Python library, and so that's why I add it here as a dependency, and more on that later in the crash course. So now I can press enter, and you can see we have some logs with a lot of stuff, but let's actually just see. So let's do clear and let's see what we have. You can see we have a new folder named My Robot Controller. And to navigate inside this, let's actually use Visual Studio Code, or you can use any text editor you want, but I'm gonna use Visual Studio Code. So to install it, let's do sudo snap install code -- classic. Okay, so now I have Visual Studio Code. That was just the line to show you how to install it on Ubuntu. And also in the following tutorials, I'm gonna show you how to configure Visual Studio Code to run with ROS2 so you can write nodes with auto-completion and everything. But for now, let's just come back to this package and let's do code dot inside the source directory of the workspace. Okay, so do I trust? Yes, I trust the authors because that's me. Okay, and this is what we have here in VS Code. So you have the source folder, and inside we have my robot controller. So if I click, I expand, and this is what I have in the package my robot controller. So everything here has been generated automatically. So let's do a quick tour of that. So first let's go to package.xml. This file will be in every ROS2 package. So that's an XML file, as you can see, and it contains the name of the package. You can also precise a version number, a description, also your email, if you are a maintainer and you are publishing the code and the license. Okay, so all of that will be useful if you decide to publish your package. So for example, if you want to publish on GitHub or in the official ROS2 repository, you will need to fill those informations. Then we have here, you can see the dependencies, and we have depend with RCLPy. This is what we have provided as a dependency in the command line. So anytime your package, so anytime the MyRobotController package depends on another package, you're going to add another depend line here, just after that one. Then we have some more stuff, and you can see we have also Ament Python for the build type. So that's a Python package. Then we have setup.cfg. This file, you're not going to touch it. It's just to help ROS2 know where are going to be installed the nodes. And then setup.py. And here you have things that are similar to the package.xml. For example, the name, the version, the maintainer, the email, the description, the license. Okay. And we are going to come back to this because actually in the entry points, that's where we're going to precise where actually to install the ROS2 nodes, but more on that later. Okay, so you have different configuration files here. Then you have a test folder. We're not gonna go into that for now. A resource folder. Okay, just leave it like this. And we have this folder, MyRobotController. So actually, this folder will be the same name as your package name. Okay, that's always gonna be the same name. And that's very important. And inside you have an init.py. Okay, and that's actually inside this folder that we are going to create our ROS2 nodes. Okay, now let's come back to the terminal. And let's go back one folder back to the ROS2 Workspace folder. Okay, very important to go to this folder exactly. And we are going to build this package. So let's do colcon build, press enter. Okay, and you might see this. Okay, so maybe the build will be successful. In this case, you can just skip a few seconds of the tutorial, but maybe you will also have an error like that. And this is because of the setup tool Python package that's not working correctly here. So I'm just going to show you now how to fix that. So let's go into that terminal and let's use pip3. Let's do list. And well, if you don't have pip3, you can do sudo apt install python3-pip. Okay, let's install it. Okay, now let's do pip3 list for all the packages, and actually let's do pipe grep setup tools. And you can see that here I have setup tools package with version, that's the version number here, 59.6.0. So if things are working correctly here, you don't need to change anything for this package. But if things are not working correctly, we will need to actually downgrade the version to the 58.2.0. So how to do that? pip3 install setup tools == with 58.2.0. Let's press enter. Okay, downloading, installing, and then let's go back to this command pip3 list grep setup tools. We have 58.2.0. So we have changed the version for the package. And now let's go back here. Let's do colcon build, and it should work. Okay, it's working correctly. You can see here colcon build successful and one package finished, which is the MyRobotController. All right, so once you see this success message, everything that's inside the package has been built. So for now we have no nodes, but if you see in the install folder, you can see we have a MyRobotController folder already. And so what's going to happen when you do colcon build? Well, it's going to fetch all the nodes and stuff that you want to install from this package, and it's going to install it inside the install folder of the ROS2 workspace. And then from there, you will be able to use ROS2 command line tools, for example, with ROS2 run that we have seen before, to start your own nodes. All right, so now we are fully ready to write some nodes. We have a ROS2 workspace that is correctly configured. We have also a package that is configured, and we can start to write a ROS2 node with Python in the next tutorial. Now let's write our first node. This will be kind of a hello world node so that you can get familiar with how to write your own nodes, how to start it, and how to use the command line tools to introspect the node. And after this node, we are gonna start our Turtle Controller project. So where to create a node? Let's go back to our ROS2 workspace. Here in the source folder, we have my robot controller package. So we go inside the package, and now, well, this package is actually a Python package. So we have specified that when we created the package. So we are going to go in the folder which name is the same as the package name. So let's go to my robot controller. Okay, so we are in my robot controller, in the source of ROS2 workspace. This one will contain only init.py. We just leave this here, and we are going to create a new Python file with touch. Let's call this my first node.py. We just create a file like this, okay? And let's make it executable with chmod +x my first node. So now it should be green here in Ubuntu terminal. All right, so that's the first step, is to create a Python file and make it executable. Then let's go back to our source folder of the workspace and let's open Visual Studio Code here. So I'm gonna do code dot. Okay, and we are in my robot controller package. So we are in the source here, the source folder, and we have my robot controller. We have just one package for now. If I open this and if I open this one, I will see my first node.py and I can start to edit the file. So let's add the interpreter line. So like this, user bin env python 3. Okay, so that's interpreter line to tell the interpreter to use Python 3. And then I am going to import rclpy. Okay, rclpy is the Python library for ROS2. So we will need to import it every time we want to create a ROS2 node with Python. Now the thing is that, well, you can see rclpy is not recognized. We don't have autocompletion. So if we want to have autocompletion with Visual Studio Code and have some nice functionalities on top of that, we can go, so let's just save the file here and we can go to this here, extensions. And I am going to search for the ROS extension. So it says, do you want to install Python? Let's just ignore that for now. And let's search for ROS and find the one with the Microsoft, okay? So the ROS extension will actually work for ROS1 and for ROS2. Okay, and that's the one we're gonna install. So let's click on install. Okay, and now it should be good. So let's go back actually to the extensions and let's see what we have installed. So as you can see, now we have different extensions that are installed. So we have ROS, we also have Python, okay, which was installed with the ROS1, okay. We also have C++, so if you want to write code with Visual Studio Code and do Python and C++, you just install the ROS extension that's gonna install Python, C++ and everything you need. So now we don't need to worry about it anymore. So you can see now rclpy is recognized and we will have autocompletion for all the features in rclpy. Great, and maybe you need to restart VS Code, depends. Here I don't need to, so I'm just gonna continue like this. Now what I will do is I will create a main function, so def main, and I'm gonna put args is equal to none. So I'm gonna allow this main function to receive some arguments, and by default I put them to none. Okay, let's just put pass for now. We're gonna fill this function later, and then let's do if name is equal to main, and let's call the main function. Okay, so this is gonna be useful when we want to directly execute the file from the terminal, for example, by just running the Python script. And having a main function just like that will be useful when we want to install the node with ROS2 functionalities. So what do we want to do in the main function? Well, the first thing to do is to initialize ROS2 communications. So to do that, we do rclpy.init, and like that. We can pass args is equal to args. So the args parameter of the init function equal the args that we get from the main. And so this is going to be the first line in your main. We initialize SCLPy, or basically we initialize ROS2 communications. The last line is going to be SCLPy dot shutdown. All right, and everything you will write will be actually here. So first line SCLPy.init, last line SCLPy.shutdown, so that you start ROS2 communications and you shut down ROS2 communications. And in between, we will be able to create a node. So the node is actually not the file itself, is actually not the program itself. The node will be created inside the program. And so for now, of course, we're going to create just one node per program. But as you get more advanced with ROS2, you will see that you can actually run multiple nodes from within the same program. All right. So let's just start with the first node now. And actually, in ROS2, the way to create nodes is to use object-oriented programming. So we are going to create the node actually outside of the main here. We are going to create a class. And this class will actually inherit from the node class of SCLPy. So we will need to do from SCLPy.node import node. And then we can create, let's say, my node. So that's going to be the name of the class. Open close parentheses, and we put node and then colon. So by doing this, we define a class myNode which inherits from the node that is from SCLPy.node. Why we do this? So that our class can already have access to all the functionalities of ROS2. Now in this class, the first thing to do is to create a constructor. So def init like this with self. And the first line in the constructor is going to be super. Okay, we're going to call the constructor of the upper class, so the constructor of the node class here. So super open close parentheses dot init open close parentheses, and here we are going to provide the node name that we want to have. So this one is the node class. Okay, it's just for programmatical purpose. That's the node class we're going to use in the program, but this is the node's name that's going to be used when we actually run the node in the graph. Okay, so let's call it, let's say, first node. Okay, I'm using on purpose, I'm using a different name for the node's name and the file's name. Okay, just to show you as an example, and I'm going to come back to this just a bit later. So by doing this, we have initialized the node, and that's the minimum you need to do to create a node. Create a class, a constructor, you call super, and you give the node's name. Now let's go back to our main here. So what do we want to do? Well, just after we initialize ROS2 communications, let's actually create the node. So let's just do node is equal to my node. And well, in the constructor, we don't have any parameters, so nothing in the parentheses here. You can add as many parameters. You can just do whatever you want. Okay, that's a class, so you can customize it as you want. But for now, we have nothing, just self. Okay, so we do node is equal to my node, and then we have created the node inside the main. So what's going to happen here? We initialize ROS2 communications and ROS2 features. We create a node that's actually inherited from the node class of SCLPy, and then, well, we're gonna run some stuff, and then at the end, SCLPy.shutdown, which is gonna also destroy the node and everything inside the node, and shut down all ROS2 communications. Now I am going to come back to this constructor, and I'm just gonna add one line so that the node can actually do something, because if we run like this, nothing's gonna happen. So let's do self.getLogger. Okay, so self will actually get the functionalities of the node class. Okay, so inside this we have getLogger dot, let's say, info, and then let's say hello from ROS2. All right, so that's the way to write a log with ROS2. From within a class, you do self.getLogger.info and some text. Let's save this, and now let's go back to the terminal. Maybe on that one, let's go to ROS2 Workspace, source, my robot controller. We have the file, let's run it. My first node. Okay, you can see hello from ROS2. We have a log with info level, the timestamp. First node is the name of the node as defined here. Okay, and then we have hello from ROS2. All right, so that's working, and we have run our first node. Okay, so actually what we have run is a Python script that we have set as an executable. So we have run a Python executable, and in that executable, we initialize ROS2, we create a node, we do stuff with the node, and then we shut down ROS2. Now, as you can see, when I run the node, we have something printed, and then we directly exit from the node. But if you remember, when we have started a few nodes previously, well, the node was continuously running, and we had to press Ctrl+C to kill the node. Here, once again, you can see the node directly exits. So what I'm gonna do, I'm gonna add, after creating the node, and of course before the shutdown, I'm going to do sclpy.spin and pass the node as a parameter. Okay, what is that? So what is the spin functionality in ROS2? Well, when you make a node spin, basically what it means is that this node is gonna be kept alive. So it's gonna continue to run indefinitely until you actually kill it with Ctrl+C, for example. And while it is alive, all the callbacks of the node, so we're gonna see later how to create callbacks for the node, so all the callbacks will be able to be run. So basically, we keep the node alive so that it can continue to run and to communicate with ROS2 functionalities until we want to kill the node. And when we kill the node with Ctrl+C, this is gonna return, and then we can do sclpy shutdown, which is gonna destroy the node here, the class and everything, and shut down ROS2 communication. So let's save this and let's go back to the terminal. Let's run it again. You can see hello from ROS2, but now we are still, you can see the node is still running. Okay, I can press enter. We are still in the node. Now I press Ctrl+C and you can see the node is killed. So we have this exception, which is not really a problem. Okay, don't worry about this, about the keyboard interrupt. It's not a problem. But you can see here that now the node is alive. And we have to kill it with Ctrl+C so that it stops. All right, let's come back to the node. Now, well, we have run the node from the terminal as a Python script, but that's not what you want to do later. What you want to do is to be able to run it with the ROS2 functionalities, for example, with ROS2 run, like we have seen before. So how to do that? We will need to, well, actually to install the node. How to install the node? Well, that's very easy. You go to setup.py of your package. Okay, so my first node is in this package. I'm gonna go to the setup.py. In setup.py here, I have entry points with console scripts. I'm gonna go inside the array of console script, press enter, add some quotes, and now what I will do is I will create an executable name. Okay, so for example, test node, and then is equal to, I will need to put my robot controller, so package name dot file name, my first node without the Python extension, and then colon main, which is actually the function we want to run. So if I go here, I have a main function. That's the one I'm gonna provide here. Okay, so test node, this is going to become the ROS2 executable, is equal to package.filename colon function we want to run. I am saving with Ctrl+S, and now let's go back to the terminal. And we are in our ROS2 workspace. In the source folder, I'm gonna come back to the ROS2 workspace here, where we have the build, install, log, and source, and I'm going to do colcon build. Let's press enter. Okay, and you can see now the package has been built. And now this is very important. After you have built the package, if you want to use new functionalities that you have developed in the package, you need to source your environment again. Okay, you need to source your workspace. How to source the workspace? You can do source bash rc, because all the source lines have been put in the bash rc. So source bash rc. Okay, and now we can do ROS2 run my, so let's use auto-completion, my robot controller. If I press tab here, we have test node. So as you can see, my robot controller, this is the package, test node. This is the node that we have created. I press enter, and you can see we have the node here, hello from ROS2, still alive, and now I can press Ctrl+C to kill the node. And so now I'm going to come back to the names here that are very important. So my robot controller, well, this is the package name. But then you can see we have test node here. We have used test node, which is the ROS2 executable. Then we have the file name, which I have named my first node. Okay, and we have the node's name, which is first node. Okay, so make sure you make the difference between the three. We have the node's name inside ROS functionalities. We have the file name where you're gonna write your code. And we have the executable name, which is the one that's gonna be installed with Qualcomm build and the one that you are gonna run. Okay, you can see here test node with the command line tool. Okay, so executable name, and then file name, and then node name. Three different things. If you want, you can use the same name for all of them, for the executable, the file name, and the node name. Okay, that's what I'm gonna use in the future actually. But here I am making it different so that you can see that there are three different things. And now a quick tip I'm gonna show you that's gonna help you to develop faster with Python. So the thing is, every time you're gonna change your Python code, you will need to actually build again, okay, with Qualcomm build, and then you will be able to run the updated version of the node. But with Python, you know that actually Python is an interpreted language, so that would be nice if we could actually skip the building part when we want to run a new version of the Python script. And how to do that? So let's first I'm gonna just change the log here, okay, just print ROS2, just to show you. Let's go back to the terminal, and now if I run the node again, well, you can see we have hello from ROS2. So this is still the old version. Okay, you can see now the code says ROS2, but we are still having hello from ROS2. So how to fix that? Let's do clear here. I am still in the ROS2 workspace. I can do Qualcomm build with symlink install. So -- symlink install. And you can see I can have the auto completion. So if you don't have the auto completion, make sure that you have correctly followed the installation steps when we created the ROS2 workspace. When I do this, okay, let's source the bash. Let's see. Now let's do ROS2 run my robot controller with test node. Okay, we have ROS2, which is, well, quite expected because anyway we have built the package again. But now I'm gonna just remove the 2, for example. I save, and now let's run again, and you can see we have ROS. So we had ROS2, now we have ROS. We haven't built the package again, but because of the symlink install option, what's gonna happen is that you will be able to directly execute the new version of your script without having to install it or to build it every time. All right, so that's quite convenient. And note that if you have some errors here, maybe you will also need to source. So when you want to modify the script, after you modify the script, you also source the bash rc and then run the node, okay, just in case if you have any problem. All right, now let's come back to the node, and actually let's make this a bit more interesting. So this node for now does, well, pretty much nothing. It just prints something and that's it, and then wait with the spin. I'm going to create a very common structure that we are going to use in the following of this crash course, and that you are going to use also all the time. So what we want to do here, let's say we want to print a message every second. For that, we are going to use a ROS2 timer and a ROS2 callback. So the principle is simple. We create a timer inside the node that's gonna say every 1 second, I'm gonna call this function, and this function is gonna do something. So let's create actually def timer callback with self. Okay, so we create a timer callback inside the node. Okay, very important, inside the node with the correct indentation. And here we do self get logger, and let's say hello. So nothing very special, we just create a function that prints hello. So actually not get logger hello, but get logger dot info with hello. And here, well, let's remove this line and let's do self dot create timer. Okay, so you have another function inside the node that is create timer. Now you need to give a timer period in seconds, and that's a float number, so let's do 1.0, and then a callback, self dot timer callback, without the parentheses. Okay, here, just the name of the function. And that's pretty much it. Let's just run this. So save and run. Let's see what it does. Hello, you can see hello, 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 etc. Every 1 second you have hello. So what happened here is that, well, we first initialize ROS2 and then we create a node in the constructor. So we set up the node with a name. We create a timer that's gonna call the timer callback every 1 second. So until now, nothing happens, but then we call lclpy.spin with the node. So the node is gonna be kept alive, and spin actually will enable all the callbacks for the node. So that's where it is super important, is that this timer is a ROS2 functionality that's gonna call a callback. This callback will be enabled because of the spin. So the spin will make sure that this node will execute all its callbacks, and so every second this is gonna be called, and we can print hello. We can also, so let's say for example we add here self.counter. I'm gonna use underscore at the end for attributes of the class is equal to, let's put 0, and then let's put hello plus str.self counter, like that. So we're gonna print the counter and then do self.counter plus 1. Okay, so the idea is to print hello 0, hello 1, etc. I save. Let's run again. Okay, hello 0, hello 1, hello 2, hello 3, etc. Well, now let's run it again, and let's run here. Let's do clear. Let's run Acuity graph. Okay, let's refresh. You can see now we have, so we have first node. Okay, that's the node that we have actually defined here. This is the first node that's running. Okay, so we can see it with Acuity graph. And for now, well, there is just one node, there is nothing else, and this node is not communicating with any other node, so that's just one node here. And I'm going to show you another command, because you have seen, so you have seen the ROS2 run command to start a node, but then you can also use, so let's do cd here, you can also use ROS2 Node. So the ROS2 Node command will allow you to introspect your nodes. You can do ROS2 Node list. You can see I have first node. You can do ROS2 Node info with the name of the node. Okay, that's gonna give you some information that we're gonna see actually later. All right, you have now created your first node and used a few of the most important ROS2 functionalities, such as logging, timers, callbacks, spin, etc. You can also start your node and introspect your ROS graph. Hey, I hope you're learning a lot, and I also hope you like this crash course. If you find it useful, then you might want to check out my complete ROS2 course, which contains more than 10 hours of structured video lessons. I will leave a link in the description if you are interested. Alright, and let's continue with the video. So now we are going to start focusing on ROS2 communications with topics. You have seen what are nodes and how to create nodes. Now let's see how nodes communicate between each other with topics, and to do that, let's simply start some nodes, and I'm going to explain it to you along the way. So let's do ROS2 run demo nodes cpp. Let's start the talker node. So this node will, as you can see, write some logs on the terminal and say publishing hello world with a number. In this terminal, let's do ROS2 run demo nodes cpp listener. So listener. And as you can see here, it's quite obvious that what's being sent, actually what's being published here, hello world 25, is received by the listener node. Okay. In this terminal, I'm going to do Acuity graph. Okay, and you can refresh. You can put nodes only, or maybe nodes topics all. So you can have the view like this. And what do we have here? Well, as you can see, we have the node talker, we have the node listener, so nothing new, and we have this box / chatter. What is chatter? Well, chatter is actually a topic. And so what's a topic? Well, it's simply a way to communicate between nodes. Okay, you will have nodes that are gonna publish. So the talker node is going to publish on the chatter topic, and the listener node is gonna subscribe to the chatter topic. Okay, so in order to make one node communicate with another one by just sending data from one to the other one, you're gonna use a topic. So the talker is actually not talking directly to the listener. The talker is publishing to chatter, and the listener is subscribing to chatter. So in the end, this data that is being sent from the talker node is going to be received by the listener, but going through this topic. Okay, let's come back to the terminal, and actually let's use some more command line tools. So ROS2, you have seen ROS2 run, you have seen ROS2 node. Actually, you can do ROS2 topic with list. And you can see we have the topic chatter. I can do ROS2 topic info / chatter. And you can see we have the type. We have one publisher, we have one subscriber. Okay, so the publisher is going to be actually this one, the talker. The subscriber is the listener. Now I can do ROS2. So this type is actually what is being sent, okay? Because there is the topic name, which is chatter, but then there is also kind of a data type that you need to respect when you publish or when you subscribe. So you can do ROS2 interface. That's going to be called an interface. Show with this. And you can see that in this, so we have some comments and you have string data. So what's being sent between the talker and the listener is actually a message called std messages / message / string, which contains the data of type string. Now let's kill this and let's kill this. So you can see with command line tools, you can actually introspect and see what's going on in your graph. You can use the ROS2 topic to see in the terminal. You can use also RQT graph to have a visual representation. Now you can also listen to what's being sent to a topic directly from the terminal. So let's say you run the talker, just the talker. The listener is not running. Let's do here ROS2 topic equal / chatter. So now we know the name of the topic because that's the one we have found here. Okay, let's press enter here. And you can see we receive data, hello world 17 here, etc., etc. And the data is here because that's actually the data type here. So the data type, so the interface is actually of type string, and the name of the message is data. So we receive data with hello world something. What's happening in the subscriber of the listener is that the message is going to be processed. Okay, so we don't have data, we just have the string here. So I can also run the listener. And you can see here we receive the message in this terminal and in that terminal. Okay, so with I can show you that with ROS topic info, we have one publisher and we have two subscribers. If I do RQT graph again, let's refresh and let's also uncheck the debug. So don't worry about this and that. What you can see now is that we have the topic chatter, we have one publisher, and we have two subscribers. We have the listener node, and we have a node that's actually being created when we create subscribers, so when we actually use the ROS topic echo comment. That's gonna create a subscriber just in that terminal, okay? So you can see that we can have many subscribers for one topic, and we could also have many publishers for one topic. And so all the publishers are gonna publish to this, and all the data is gonna be sent to all the subscribers. So this subscriber is gonna receive the same thing as this subscriber, for example. Now if I, let's say, kill this one, I go back to RQT graph, I refresh, you can see now we don't have this node anymore, we just have the listener. I'm gonna remove debug, okay. Now, okay, that was the first example. Let's use another example. So let's clear this. Let's come back to the turtle sim. So ROS2 run turtle sim with turtle sim node. Okay, so we have the turtle sim. Let's put that actually on the side. And in this one, let's do ROS2 run turtle sim. And what do we have? We can also run the turtle teleop key. Okay, and with this, if I select this terminal and I press the arrows of the keyboard, I can make the turtle move. Okay, now here let's do Acuity graph. Let's actually refresh. And okay, you have group 2, let's go to 0. Okay, so that the view is gonna be maybe a bit more simplified. So what do we have here? We have two nodes. We have the turtle sim node and we have the teleop turtle node. And so what's happening? What's happening is that you can see that what we have in this node, so with the turtle teleop key node, is gonna be sent to the turtle sim node, okay? Because when we actually press the keys on the keyboard in this terminal, the turtle is moving, but the turtle is handled by this program, okay? So two different nodes. So you can see here clearly with the Acuity graph that this is gonna be actually here, turtle1/cmd vel for command velocity. So we have a topic, turtle1 command velocity, and so the teleop turtle node is gonna send some message, so it's gonna publish some message to this topic, and the turtle sim node is gonna subscribe, so it's gonna receive messages from this topic. And this way, this node can actually talk to that node. And you can see we have other topics, so I'm not gonna give more details about this, but you can also see that this node, turtle sim, is also sending messages to the teleop turtle, okay? So you can have different topics, and you can have even like a closed loop control if you want between two nodes, okay? One node can send some data to the other node, and this node can also send data to that one, okay? So we can have like a closed loop control. But for now, let's focus on that topic here. So this node is sending data to that node. If I do ROS2 topic list, I can see here turtle1 command velocity. So I can do ROS2 topic info / turtle1 / command velocity, and I can see I have one publisher, one subscriber. The publisher is that one, the subscriber is that one. The type of the data is this one. So I can do ROS2 interface show with the type, and I can see that this interface is actually a vector3, so that's another interface, linear, which contains x, y, and z, and angular, which contains x, y, and z. So that's a command velocity to give a linear velocity, okay, following 3 axes, and an angular velocity following also 3 axes. And so this is what is being sent actually from this node to that node. All right, so basically put, a topic is a way to communicate between different nodes in your ROS application. Nodes actually don't directly talk to each other. They just publish or subscribe to a topic. You can have multiple nodes publishing on the same topic and multiple nodes subscribing to the same topic. So a topic has a name, which is kind of actually the address of the topic, so the nodes know where to publish or where to subscribe, and they have a data type, so they also know what to send and what to receive. The topic mechanism is anonymous, which means that, for example, if a node is subscribing to a topic, it is just going to receive the messages from that topic. It doesn't know which node is publishing them. So now that you have a basic understanding of ROS topics, let's write a topic publisher in a Python node. So to create a Python node, the first thing is actually to create a Python file. So let's go back to our ROS2 workspace, source directory, my robot controller. In this we have for now, well, my first node.py. Let's actually make that a bit bigger. And what we can do is to create another one. Let's say touch draw cycle.py. So what we will want to do here is to control the turtle So with the turtle sim node, we are going to control the turtle to make it draw a cycle. Okay, so we will not have to actually run the teleop key and press some keys on the keyboard. Everything is going to come from the code that we write. And I do chmod plus X. So now this is an executable. All right, let's go back to the source folder and let's do code dot, and we can edit the file. So my first node, we don't need it anymore. This one for now, no. Draw cycle. And so let's just init the node. So first, the interpreter, user bin env python 3. And we are going to import rclpy, okay? Also from rclpy.node import node, because we're gonna use the node class. And then let's do def main with args is none. Okay, so now I'm gonna go just a bit faster because we have already actually created a node here. So make sure that you have correctly followed the previous lesson on how to create a node with object-oriented programming. In the main function, let's do rclpy.init with args is equal to args. And then rclpy.shutdown. Okay, so that's the first thing to do. Then if you want to also run the script from the terminal directly, you can add if name is equal to main, call the main function. But I'm not gonna do it here. So let's just keep it like this. Now I'm going to create a node. So class, let's name it simply draw cycle node, which inherits from node. Let's create a constructor, init self with super.init, and let's call this node draw cycle. As you can see here, I use the same name for the node and for the file. Just make sure that you know, of course, that this name is different from that name. Okay, those are two different things. You can use the same name if you want, but this is the file name and this is the node name. And then maybe let's do self get logger dot info node. So maybe draw cycle node has been started. Okay, I like to have a log usually in the constructor of the node so that you can see when you actually start the node that the node has been started and that it's running. Okay, so now we have initialized the node. We still don't have any publisher. So let's create a publisher. The publisher will allow us to send some messages to a topic. So how to create a publisher in ROS2 with Python? Well, let's create it here. You can do, for example, self. So let's create an attribute. Let's call it command vel pub, like that. So cmd vel, so command velocity pub is equal to self. So you can use self create underscore publisher, as simple as that. The self is the node, so the rclpy node, and you create a publisher. Let's open and close parentheses. And then what do you need to give? You need to give first the message type. How to know the message type? Well, we have seen that in the previous tutorial. Let's come back to the terminal and let's run. So let's run turtle sim here. ROS2 run turtle sim node. Okay, so we have the turtle. Now let's reuse here the ROS2 topic list. You can see that this is the topic we want, turtle1 command velocity. So if we do ROS2 topic info with that name, now you can see we have the type. Okay, the type is geometry messages, message twist. So that's what we need to send, a twist message from the geometry messages package. All right, so to do that, I'm gonna come back here and I'm gonna do this here from geometry messages dot msg import twist. And you can see we also have the auto completion because the geometry messages package Okay, where is this package? Well, this one was actually installed when you installed ROS2 with your global installation. And I can put here twist. Now, one very important thing is that because I'm using geometry messages package in my robot controller package, so let's go to package.xml and let's add a depend tag after RCLPy. Depend geometry MSGS. Okay, so any package that you're gonna use in my robot controller, you're gonna also add a dependency here in package.xml. And by the way, I can also add turtle sim. Because for now we don't explicitly use turtle sim here in the code. We're gonna do that later, but we actually need turtle sim to run because we're gonna send some command to the turtle with the turtle sim package. So I also add dependency to turtle sim to make sure that actually when we run something in this package, we have so the Python library, RCLPy, the geometry messages, and the turtle sim packages. Let's save this, and that's pretty much it for the dependencies. Okay, so now I have the message type. Now I need to give the name of the topic. Okay, so a topic has a message type and a name. So what is the name? The name is that one, turtle1 command velocity. So let's just use the same with quotes. Okay, and make sure you use the exact same name. Okay, any typo here and it's not gonna work. Okay, and finally I will add 10 here. So what is this? Well, this is a queue size. Okay, so you need to precise a queue size. So basically, but let's say that you are sending some messages on a topic in a network that is not that reliable, or you are sending big pieces of data, the queue size will kind of create a buffer, okay, so that you can make sure that all the messages are gonna be sent. And so the buffer here will contain 10 messages. So it's not really important for now, you just have to provide it. Let's just use 10 every time. And then when you get more advanced with ROS2, you can actually know more about this and use the settings that's gonna work better for your application. All right, so create publisher with the data type and then the topic name and 10 for the queue size. So we have a publisher now. Well, this publisher will not do anything by itself. So we need to publish some data. And what we are going to do is, so let's say we want to send some data. So we want to control the turtle. We want to send some data every 0.5 seconds to give an instruction to move. So how to send some data every 0.5 seconds? Well, let's just use what we did before. Let's just use a timer with a callback. So let's do def. Let's create a callback. Let's name it, for example, send velocity comment. So actually we just create a normal function. And how to actually send something to the topic? So we have the publisher, but how to send something? Well, we will first need to create a message. So the message is equal to twist. So we use twist with open close parentheses to create a message object from the class twist. And now we will need to fill this. So how to know what we need to send? Well, let's go back to the terminal and let's do ROS2 interface show to see the inside of the interface. And now you can see we have vector3 linear, so that's another type. So we have linear and then x, y, and z. So we will have linear.x, linear.y, linear.z, and the same for angular, angular.x, y, and z. Now, if we look at the turtle sim, so this message is actually a 3D message, but here we are in 2D. So we will only be interested in a few of those. For example, the linear x. So the x-axis here will depend on the turtle. Okay, so from the turtle going forward, this is going to be x. Okay, going perpendicular here, this is going to be y. Okay, so if you send a linear x command, you're gonna tell actually the turtle to move forward. So if it's positive, and to go backward if it's negative. Okay, so that's a command we want. And then if you send an angular velocity, well, because this is 2D, the only angular velocity we can send is the z axis. Okay, the z-axis is basically to turn on itself here. So by just sending a x linear velocity and a z angular velocity, we will be able to make the turtle just turn around. Okay, I'm not gonna go into more details about this. This is just mathematics. And here the most important is actually to understand how to use ROS2. Okay, so let's go to the code and let's do msg dot. And you can see here you have linear or angular. So we already have the auto completion with the twist. So let's do linear dot x is equal to, and let's use 2.0. That's the value I have tested before. You can also test different values if you want. And then let's do msg dot angular dot z is equal to 1.0. Great, so now we have created a message. We have filled the data of the message, so you don't necessarily need to fill all the fields, okay, just the one you want. All right, so we have created the message, and of course what we need to do is to publish the message. So how to publish the message? We do self dot command vel pub, so the publisher we have created dot publish, and we pass the message. All right, so we create a publisher, and then we create a message, and we use the publish method of the publisher to send the message. As simple as that. And now, well, this node is still doing nothing because it creates a publisher, it prints some log, but we are not publishing anything. So here I'm gonna do self timer is equal to self create timer. I'm gonna give 0.5 seconds, and the callback is self send velocity command. All right, so when the node is created, we're gonna create inside the node a publisher and then a timer and print something. The timer is gonna call this function every 0.5 seconds, and inside this function we create a message, and we use the publisher that we have created here in the constructor to publish the message. So that's it for the node code. Now let's go back to the main. What do we have? We initialize ROS2, we shut down ROS2. Let's create the node, draw cycle node, and let's do rclpy dot spin with the node. That's it. We create the node and we make sure to, of course, spin the node. If we don't make the node spin, well, we're just gonna exit the program right now. If we make the node spin, it is going to be kept alive, and this timer will work every 0.5 seconds. So this is gonna be called thanks to the spin method here. So let's save this, and now let's go to setup.py to actually install the node. So how to install the node? Well, we're gonna do the same thing as here in console script. We're gonna add another line. So go after this one, make sure you add a comma. That's very important. If you forget this comma, you will have some weird errors after that. And let's add another node, so another executable here. Let's name it draw cycle is equal to my robot controller dot draw cycle colon main. So what do we have here? This is gonna be the executable name draw cycle is equal to package name dot file name. Okay, you can see here the file name is also the same as the executable draw cycle, and then colon main because we want to call the main function. All right, so let's save this as well. Let's go to the terminal and okay, let's kill this. Let's go back to ROS2 Workspace and let's do colcon build, and I'm going to also do symlink install. So the symlink install will allow us, as you have seen before, it will allow us to modify this file here and not having to build again to run the updated version of the node. And the thing is, we still have to actually use colcon build because, well, the first node, my first node was already here, but draw cycle was not here. So when you create a new file and you create here a new executable, you need to do call build. The symlink install will only work for executables that are already created. Okay, so let's do this. Okay, finished. It was very quick. Now let's run the TurtleSim node. Okay, so we have the TurtleSim node, nothing happens. In that terminal, let's do source -sc, okay, to make sure that we have set up the ROS2 workspace environment. And let's do ROS2 run my robot controller. I'm gonna press tab twice. You can see now we have two executables, draw cycle and test node. So I'm gonna run draw cycle and let's look at what's happening here. The turtle is drawing a cycle. Okay, and is cycling around. So if we want to debug this, let's do clear. So if we want to do some introspection, let's do acuity graph. And let's refresh here. And you can see we have our node named draw cycle. We have the TurtleSim node, and the draw cycle is publishing to the Turtle1 common velocity topic. The TurtleSim is subscribing to this topic so that this node is actually sending data to that node. Great. Now let's say I kill the TurtleSim. Okay. Well, this draw cycle is still gonna send some data to the Turtle1 common velocity topic, but there is no subscriber, so nobody's gonna receive it. Now I can start the TurtleSim again, and you can see the turtle is gonna continue to move. So let's put the turtle here. If I stop the draw cycle node, you can see the turtle is gonna stop. I start it again, the turtle is gonna move, and I stop. Okay, it stops. And so the very important thing here is that you need to pay attention to, let's go back here, you need to pay attention to the type you're sending and the name, okay? This is the most important thing. You use the exact same name and the exact same type, otherwise the communication is not gonna work. And let's come back very quickly and let's run the turtle again and the draw cycle. Okay, so it's working, and here let's do ROS2 topic list. You can see we have common velocity still here, ROS2 topic info with that one. You can see now we have one publisher, one subscriber. If I do ROS2 topic echo with that topic, you can also see what we receive. Okay, so we receive some messages. I'm gonna do Control-C. You can see we will receive some messages with linear x is equal to 2, and then we have 0 and 0, and then angular z is equal to 1. That's exactly what we are sending here. Okay, so if you want, you can experiment with different values to make different cycle, and well, congratulations, you have written your first ROS2 publisher. In the last tutorial, you have created a Python publisher. So now we are going to create the other side of the communication, which is a subscriber. So in our Python code, we will be able to receive data from a topic. And now, before we even start, we need to know what kind of data do we want to receive, what topic do we want to listen to. So I'm gonna run the TurtleSim, so ROS2 run TurtleSim node again. Okay, we have this, and if we do ROS2 topic list, let's see what do we want to receive. So here, common velocity is actually to send data to the TurtleSim. The pause is actually published by the TurtleSim node. So if I do acuity graph, okay, let's refresh. And if I uncheck those boxes here, dead syncs and leave topics, you can see now, so we have the TurtleSim node here, which is subscribing to common velocity, but the TurtleSim is also publishing Turtle1 pose. So the pose is the current position, so pose is position and orientation of the turtle. We have also other topics, but let's focus on that one. So for now, the TurtleSim is publishing to that topic, but there is no subscriber, so the messages are just not used. I can do, for example, ROS2 topic echo with the pause. Let's see what we get. You can see we receive very fast messages with the X, Y, theta position. Okay, so that's the X axis is going to be this one, the Y axis is going to be that one, and the theta is going to be the orientation. So 0 is looking forward here to the right. And we also have linear velocity and angular velocity. So let's say we want to create a subscriber to get the current X and Y position of the turtle in the window here. So we will need to subscribe to, let's come back here, to the turtle1 pose topic. Now we need more info, so let's do ROS2 topic info. So you see for now we have one publisher, and you can see that this is the type, turtle sim message pose. And we can do ROS2 interface show with this. And you can see inside we have float 32, so that's the float number, X, Y, theta, and then linear velocity, angular velocity. That's actually what we have found also here. So now we have all the information we need. We have the name of the topic we want to subscribe to, we have the type, and we know what's inside the message. Now we can start to write some code. So, well, let's actually kill that, and let's go to our workspace again, my robot controller and my robot controller, where we have all our Python files. Let's do touch, actually just like that, touch pose subscriber. Okay, let's keep things simple here, and chmod plus x pose subscriber. Great. Now let's go back to source repository and code dot to start Visual Studio Code here. Okay, and we have this new file, post subscriber. Now we can init. So let's init the file and the node. So user bin env python3. We will need, as always, to import rclpy. And because we are going to create a node, from rclpy.node import node. Now let's create a main function. Args is equal to none, so I'm gonna go quite fast here. rclpy dot init with args is equal to args, and rclpy dot shutdown. Okay, and everything will be in between. So we have our main. Let's create a class. So how do we name this class? Well, let's do post subscriber node, which inherits from node, and def init. So that's the constructor. We call super dot init, and we name the node. Also keep it simple, post subscriber. Okay, so now we have the basic code for the node. What we want to do is to create a subscriber to a topic. So how to create a subscriber? So let's create an attribute here in the constructor, self.pose subscriber is equal to self. So it's quite easy. To create a publisher, you do self.create publisher. Here you do create subscription. Self.create subscription, you open close parentheses, and what do you need to give? First you need to give the message type. So what kind of message do you expect to receive? If we go back to the terminal, in that one, you can see the interface is turtle sim message pose. So let's just include that. Let's do from turtle sim.msg import pose, and we can put pose here. Note that because we use turtle sim, we need to go to package.xml, and it's already here, so we already have the dependency, nothing else to do. So great, we have the type, and then, well, guess what? The topic name. So what is the topic name? The topic name is that one, turtle1. So with the slash, turtle1 pose here. Okay, let's actually go back to a new line here, so that is more readable. And then the third parameter here will be a callback. Okay, why a callback? Because actually when you create a subscriber, you're gonna receive the messages and you want to process the messages when you receive them. So you're gonna create a callback. So you're gonna create a function that's gonna act as a callback, and that's gonna be called every time you receive a message on that topic. So let's name this one pause callback with self, and we are also going to receive a message. So let's put msg, and the message is gonna be of type pause. So you can use that with Python to make it easier with :pause to tell Python here that you're gonna get a message as a pause object. So you can have auto-completion here in the function. All right, and what are we gonna do in the callback? So the callback is gonna be called when we receive a message. So let's just print the message. Let's do self get logger with info, and let's do str message. So just the string representation of the message, and we will see later how to process it a bit more. But for now, let's just print the message we receive. Okay, and in the create subscription, we have so message, topic name, and then the callback self dot pause callback. And then I'm gonna add 10 also as a queue size. So if you remember, that's kind of a buffer. So if you can't receive all the messages immediately, for example, if you have a lossy network or if the messages are too big, this is gonna create kind of a buffer. So I'm just gonna put it to 10 for now and forget about it. That's not really important at the beginning. All right, so quick recap to create a subscriber. So you create an attribute here in your node, and you do self.create subscription. First with the data type, then the topic name, then a callback and a queue size. For the callback, so what I usually do is I call it, so what I'm gonna receive, underscore callback. So that it's easy to know that this function is actually a callback. And then in the callback, you have one parameter, which is the message you receive. And with the message, you can do whatever you want. Now, in order to make this work, I will need to create the node here. So node is equal to pause subscriber node and do rclpy.spin node. That's very important because if you don't make the node spin, well, you're just gonna create a subscriber, but then that's it. The node is gonna be killed and rclpy.shutdown. With the spin, the node is gonna be kept alive, and whenever you receive a message on that topic, this callback will be called thanks to the spinning functionality. Okay? So let's save this and let's try it. Let's actually install it. So let's go to setup.py. I'm gonna add a comma here, new line, and let's do pause subscriber is equal to my robot controller dot pause subscriber colon main. So pause subscriber is gonna be the executable name, then package name dot file name, which is that one, colon main for the main function. And then inside the node name here is gonna be also pause subscriber. All right, so let's go back to the terminal, and we will need to go back here to the ROS2 workspace and do callcon build, and I'm also gonna put symlink install. Okay, so I'm building this new executable, and with symlink install I can modify it and not having to build it again. So let's do source bash rc, make sure that we source the environment, and let's do ROS2 run my robot controller with pause subscriber. Okay, so the node is running. We have actually nothing. Why is that? Because, well, we create a subscriber and we have a callback and we spin the node. That's it. So if we don't receive any message, well, nothing's gonna happen. But the node is still here. Now on this terminal, I'm gonna do ROS2 run turtle sim with turtle sim node. Let's put that here. Okay, we have the turtle here, and you can see now we start to receive messages on the pause subscriber. Okay, we will receive a pause with x, y, theta linear velocity and angular velocity. Okay, because now this node is publishing to the topic pose. Let's check with RQT graph. Let's actually refresh. Let's remove dead things and leave topics. So let's actually check the boxes. Now you can see the turtle sim is publishing to the turtle1 pose and the pose subscriber is subscribing to this. So it's just like the turtle sim node was sending messages to the pose subscriber. So we can communicate between the two nodes. And now in this, so if I kill actually the turtle sim, you can see we stop receiving messages. If I start again, we start receiving messages again. And now in this terminal, let's do ROS2 run my robot controller with draw cycle. Now you can see the turtle is moving, and also here we will receive the pose, and you can see the X, Y, and theta are also moving. Why is that? So let's actually restart RQT graph and let's refresh. You can see now we have the draw cycle, which is publishing something to the command velocity, which is then received by the turtle sim. And then the turtle sim is publishing on the pose topic, and the pose subscriber is subscribing to the pose topic. So when the draw cycle is sending some command, the turtle sim is gonna move the turtle and is also gonna update the pose so that the pose subscriber is gonna receive new updated data. And let's come back to the code here actually. So we just print for now the string representation of the message, but let's say we want to actually do more stuff and get the fields of the message. So we can do that. For example, let's actually modify the way we print. Let's just print X and Y with a nice syntax. So let's put the parentheses and then str with message dot, and we can get access, for example, to message.x. Okay, and then plus, let's put a comma, plus str message.y, then plus, let's finish with a parenthesis. Okay, so you can access each attribute, so each field inside the message. And then, well, I just print this, but you can do whatever you want. Okay, you can update an attribute in the class, you can decide to call different functions depending on what you receive, etc. So now let's save this and let's actually go back here. I'm gonna kill this node. I'm gonna source the bash sc, and I'm gonna do ROS2. So I'm just gonna run the node again. And you can see now we receive not just the complete message, but X and Y. So the turtle is still moving. Yes. And so we receive X and Y just like that with parentheses. All right, and you have created your first ROS2 subscriber. Wow, you are still here. Congratulations. Why I say that is because many people give up on tutorials after just a few minutes. But you have made it until this point, and I have a feeling that you're going to continue and finish this ROS2 crash course. If you are enjoying this tutorial so far, you can check out my full course on ROS2, which actually contains more than 10 hours of video content. I will leave a link in the description if you are interested. Alright, and let's continue with the video. As for now, in this tutorial series, we have created one publisher in one node and one subscriber in another node. But we can do better than that. We can create one node which is going to contain both a subscriber and a publisher. And in this particular case with the turtle sim, what we are going to do is to create a closed loop system for the turtle. So first of all, let me show you what we are going to do and what topics we are going to use for this closed loop control. Let's run, so ROS2 run turtle sim with turtle sim node. Okay, we have the turtle, and then let's do RQT graph. Okay, so we have just the turtle. Let's actually uncheck dead things and leave topics, so we can see all the topics even if there is no publisher or there is no subscriber. And now what do we want to do? Well, we want to control the turtle sim with a closed loop control. So we want to control actually the turtle in the turtle sim node. What we will need to have, we will need to have actually the pose of the turtle to know where the turtle is, and we will need to send commands to actually this topic, command velocity. So we will create a node somewhere here that's gonna subscribe to the pose, and publish to the command velocity. And this node is going to monitor the pose, so receive current position, and send an appropriate command depending on what it has received from the position. Okay, so the loop will be like this, closed loop control like that. And basically what we are going to do in this controller is we are going to say to the turtle, just move forward, and then we are going to define some borders which are not, so not this border and not that border, but a bit before, so that the turtle can actually turn around when it gets closer to the edge of the window, turn around and continue to move, for example like this, and then turn around, continue to move, etc. So that the turtle can continuously move forward and turn around when it gets closer to any of the edges of the window. Alright, so now that we know what we want to do, let's actually kill the node and kill our Qt graph. Okay, and let's now create a new file. So we are going to go to our Workspace source folder, my robot controller. We have already 3 Python files. Let's create another one, touch. Let's do turtle controller.py, and then, so let's actually put this here, chmod plus x with turtle controller. Okay, now let's go back to our source folder and let's do code dot to start Visual Studio Code in the source folder of our workspace. So we don't need this anymore. Okay, and now let's edit the turtle controller.py. So first things first, let's initialize the node and the file. So that we've already seen several times. So interpreter with Python 3, and then let's import rclpy. Let's import, so from rclpy.node import node. We are going to create a main function with args none, so that's gonna be the same all the time. All right, rclpy.init with args equal args, then rclpy.shutdown. Okay, I'm not gonna create if name is equal to main, so I'm not gonna do like my first node here, because we are not gonna launch directly the file, we're gonna install it, so I just need a main function. Okay, let's create a node. Let's name it turtle controller node, which inherits from node, and then def init self. We will need to call super dot init, and let's give it a name, turtle controller. Okay, let's keep things simple, and then maybe do self.get logger with info turtle controller has been started. Okay, now let's complete the main. Node is equal to turtle controller node, and then rclpy dot spin with the node, and that's it for the initialization. Actually, we can also, so let's save and let's install it directly. So we add a comma here, and then turtle controller is equal to my robot controller dot turtle controller with a colon and main, and let's save it. Okay, now let's go back to the terminal. Let's go back to our ROS2 workspace and let's do colcon build -- symlink install. Good. Now let's do source bash rc and ROS2 run to see if we correctly initialize the node with turtle controller, and yes, we can find it. Turtle controller has been started. Now the node is spinning. Control C to quit. All right. And let's now start the control of the turtle. So we will need to create a publisher to the command velocity topic, and we will need to create a subscriber to the pause topic. And actually, how we are going to manage things is that we are not going to, so let's see what we did in draw cycle. In draw cycle, if you remember, we created a publisher to the command velocity topic, and then with a timer that was running here every 0.5 seconds, we were publishing some velocity. But we are not going to create a timer here. What we are going to do is we are going to create a subscriber to the pause topic, and in the subscriber callback, we are going to publish actually to the command velocity. Okay, so whenever we receive a pause, we publish a new comment. So let's start actually with the subscriber, and we're going to create a subscriber. So we actually already know what we need to do here. I'm going to go back to the terminal to find the name and the type. You can see the name is turtle1 pause and the type is turtle sim pause. So let's do from turtlesim.msg import pause, and then let's create a pause subscriber is equal to self create subscription, and the type is going to be pause. Actually, let's go back to a new line here, and then the name is going to be, let's just use the same name exactly. Okay, turtle1 pause, and then we need a callback. So let's create def pause callback with self, because we're in a class, and then pause. So we could put MSG, but I can also put pause, the same with colon and then pause, so that we say that this is a pause data type, which is going to help for the auto completion. For now, let's just use pass. Okay, let's keep the function empty and let's put it there. So self pause callback, and then 10 for the queue size. All right, so self create subscription, message type, the topic name, the callback, and then queue size. And just like this, the subscriber should work because, well, we have a subscriber, a callback, and we are spinning the node. Now, let's create the publisher. So I'm going to create a publisher here before the subscriber, self. So command vel publisher is equal to self.create publisher. What message do we need? So let's actually go back to draw cycle where we actually did the same thing. We need a twist message from geometry messages, and the name of the topic is turtle1 command velocity. So let's do that from geometry messages.msg import twist. I'm going to put twist here, twist. Actually, let's also go back to a new line for readability. The topic name is turtle1 command velocity, written like this, and then let's put 10 as the queue size. Good. So we have created a publisher and a subscriber. Now, what do we need to do? We need to publish something new when we receive a pause. So here we will need to check actually what is the current pause of the turtle, and depending on the pause, we may send different comments. But just to try and to make sure that we are actually sending some comments when we receive a pause, let's just send a very basic and stupid comment to the turtle just to check that our code is working and that the callback is working, okay? Step by step. When we are sure that this is working, then we can think about what's the best way to control the robot, okay? So let's actually create a comment. So I'm gonna use comment is equal to twist. Okay, we receive a pause here, and we're gonna create a comment that is actually a twist, all right? And now in the twist, what do we have? So let's do comment dot. We have angular and we have linear. So for this first step, let's say that we just want to make the turtle go forward. Even if it hits the wall or the edge of the window, that's okay. We just want to make it go forward. So I'm gonna do command linear dot x is equal to, and let's use 5.0 as a velocity, and then command dot angular dot z is equal to 0.0. I'm gonna leave the other one to 0, so no y and z linear and no x and y angular, okay? I'm just gonna focus on the x linear and the z angular, like I explained before when we did the draw cycle node. So we have a twist command. Now I can do self dot command vel publisher dot publish with the command. Okay, so here we don't use the pose yet, but we just publish when we actually receive a pose, so in the subscriber callback. Okay, so this should be okay. Let's save the file and let's go back to the terminal. I'm gonna move it like this. Okay, clear. Let's actually do cd and source the bash rc. So I don't need to build anymore because I've used symlink install. Let's just make sure that we source the bash rc. And okay, in this terminal, let's do ROS2 run turtle sim node. Okay, we have the turtle right there, and in that one, let's run the controller. So ROS2 run my robot controller turtle controller. And now let's look very closely at what's gonna happen to the turtle here. I press enter, and okay, the turtle is moving forward and then hitting the wall. Okay, and you can see I hit the wall, etc. So the thing is that it's working. It is doing exactly what we wanted to do, which is that when we receive a pose, so here with the pose callback, we send a command to go forward. So that's exactly what the turtle is doing. And that's already a good progress in this application. So now what we want to do is we want, of course, to not make the turtle hit the wall, but to actually, let's say, to turn around when it gets closer to the wall and then come back and continue and just continue to move indefinitely. And so to do that, we will need to know what are the coordinates. And so I'm going to show you very quickly what are the coordinates. So let's just kill everything. Let's start the turtle sim again. And here I'm going to start the teleop. So ROS2 run turtle sim turtle teleop key, so that I can move the turtle. And when we move the turtle, we also want to know what are the coordinates of the turtle. And so to get the coordinates, well, here let's do clear and let's do ROS2 topic list. We have the pose that we can subscribe to. And in the pose, you have the X and the Y. But also, if you remember, what did we do before? We did a pose subscriber. And in this pose subscriber node, we actually filter the pose to just bring the X and the Y coordinates, which is basically what we want to know right now. So I'm going to use this instead. ROS2 run my robot controller with pose subscriber. Good. And you can see we have so the X here and the Y. And so what you can see is that the turtle is now in the middle at about 5.5 and 5.5. So 5.5 on the x-axis, 5.5 on the y-axis. Now let's move the turtle. So let's make it go forward and hit the wall. You can see now we are at 11, so just about 11 on the x-axis. And we are still at 5.5 on the y-axis. Okay, so let's go to the upper right part. Okay, we are at 11 and 11. And let's go to the other diagonal. Okay, so let's go to the bottom right. Let's focus here. Okay. And we should reach 0 and 0. Yes, okay. So you can see, I'm gonna stop this one. You can see that in this window, we start at 0, 0 here. And then on the x-axis, we go until 11. On the y-axis, we go until 11. So we know what are the coordinates that the turtle can reach. And so what we could say now is that if the turtle is close to the border, let's say by 2, so if the turtle reaches, for example, x, which is 9 or more, then it should turn around. Then we can do the same with y is more than 9. We could do the same with x is lower than 2. And we could also do the same with y is lower than 2. So we can make sure that we actually kind of draw the square inside the square. This is gonna be the safe square where the turtle can just move forward. And when the turtle goes outside of this, which is closer to the actual border of the window, then we make the turtle turn around. Okay, so again, let's do step by step. Let's actually start the turtle sim and let's imagine the current scenario. So the turtle is going forward. Okay, and let's just make it turn when it reaches this wall on the right. And that's it. All right, so let's stop this and let's stop that and clear everything. And let's go back to the code. So we are going to improve this pose callback. And here we will need to use actually the pose. Okay, we will need to use the current position of the turtle. So what I could do here is to check that if pose dot x, okay, we have the x coordinate is greater than 9. So greater or equal, it doesn't really matter here. So if the x coordinate is greater than 9, what do? We make the turtle move in a circular way. Maybe let's actually create the command first and then check this. So let's do command dot linear and let's also make the turtle go slower. So I'm gonna use linear x is 1.0 and then command dot angular dot z is equal to 0.9. So why those values? Well, those are values that I've tried before actually and that I know are working. So if you want, you can just start with those values and then increase a bit the x or z velocity or decrease them, all right, to find something that works. But by doing this, you can see here we move at 5. So the speed is 5 for the x linear. Here the speed is 1, so it's gonna go slower and it's also going to turn on the z axis. And so if the pose is greater than 9, we do this, but then we need to do also else, and I'm gonna put this in the else. So we only go forward if the pose, so if the x pose is not greater than 9. All right, so we have two different commands depending on the current pose. And then we, of course, publish the command. So let's save this and let's see what we have. Source /rc here. Let's run the turtle sim and let's run our controller. So not post subscriber, but turtle controller. Okay, good. You can see it's turning and then it's going again, and of course it's gonna hit the wall because we haven't specified what to do if the x is lower than 2. So as you can see here, the turtle was going forward because the x is lower than 9. When x reaches 9, we change the command. So instead of going to 5 speed on the x-axis, we go to 1, and then we also add an angular velocity. So the turtle is going to turn until, well, actually until the x pose is lower than 9, and in that case, we just continue to go forward. So now what we need to do is we need to handle the case for the left part, for the top part, and for the bottom part. And that's gonna be actually quite easy. So we can say if the pose is greater than 9, or the pose x is lower than 2, or the pose y is greater than 9, or the pose y is lower than 2. And that's it. Okay, so if we do this if, we check that actually the turtle is close to the wall. Okay, so either the x or the y is lower than 2, or the x or the y is greater than 9. In this case, we make the turtle rotate. Otherwise, we just continue to go straight. Let's save this. Go back here. Let's kill this one. Source /rc. Let's start the turtle sim node again. And the controller again, and let's see what's gonna happen. Okay, we turn here and then go straight, and then we turn, and then go out of this. Let's turn, and you can see it's turning again. So here it's hitting the wall a bit, but that's okay. Okay, and we turn again, etc. So for example here, I'm gonna stop the controller, and you can see when I stop the controller, well, the turtle just stops moving. So you can see here we hit the wall, and if you want to avoid that, you may want to actually increase the angular z velocity here. But if you do so, for example, I'm gonna do 1.5, okay, and let's see what's happening. So let's start the turtle sim, and then I'm gonna source the bash rc and do the turtle controller. Okay. What may happen is that the turtle at some point, so let's wait a bit. Okay, you can see this behavior is that the turtle is actually gonna be stuck, because if it turns too fast, it may stay over the limit, and the limit here is y9. So the turtle is over the limit and is stuck. So that's why I have actually reduced the angular z to 0.9, because that's a value I found that works. You could go down even to, for example, 0.8 or 0.7, and that's okay. Even if the turtle hits the wall at some point, that's really not a problem. Okay, we are experimenting with ROS2 here. That's just a simulation. All right, so let's run it again, actually. So let's kill this and then do source bash rc, run the controller. So we can start to run the controller actually before the turtle sim node. It doesn't matter, because it's only gonna wait for the pause and then send some comments. So nothing's gonna happen until we start the turtle sim node. So let's wait. I'm gonna wait maybe 1 minute and show you what it's gonna do. Well, and as you can see, the turtle is continuously moving and turning when it reaches the edges. All right, so everything is working correctly. And let's just run RQT to finish here. And now we can remove dead things and leave topics. And you can see we have our closed loop control. So we have the turtle sim here and the turtle controller node. And you can see the turtle controller is listening to the pause and then sending data to the command velocity. So we have a closed loop control here. So in this tutorial, you are going to understand what are ROS2 services. And to understand what are services, let's start with the problem. So let's say you have different nodes and you want an interaction that is kind of a client server. So you want a node to act as a client. So it's going to send a request to a node with a server, and then the server is going to process stuff and reply to the client. And this kind of interaction, well, is not really what topics are made for. Okay, with a topic, as you have seen, you send some data from one point to another point, but you don't get an answer. Okay, we can do a closed loop system, but you can't have this client-server architecture with a request and a response. And so that's why we have ROS services. So let's run a few services and you will quickly understand, and then everything will make more sense. So in this terminal, I'm gonna run, so ROS2 run demo nodes cpp. Let's come back to this package, and here we have add to int server. Let's run that. So when I run it, nothing happens. You can see I press enter. The node is just waiting. So this is a node where we will have a service. Now, if I do RQT, the thing is with RQT, you can't see services. Okay, you can see nodes and topics, but you can't see services. So RQT will not be useful for services. But we also have ROS2 service. So we have the ROS2 topic command for topics, and we have ROS2 service for services. And you have ROS2 service list. And you can see we have add to int service. So a service will have a name, just like a topic has a name and a type, while a service will also have a name and a type. And here you have, well, you have stuff that is specific to the node add to int server. Okay, so if I do ROS2 Node list, you can see we have add to int server node, and for each node you will have a set of services. But we don't really care about those. What we want is this one, add to int service. And so how to get more info about this service? Well, ROS2 service. And then you can see we have actually type, okay? So when I press tab, I can see type and this. So you can see that the type for the service is example interfaces, SRV for service, add to int. So how can I see what's inside? ROS2 interface show. So just like we did for messages with topics, we can do ROS2 interface show for services. And let's put this, and you can see we have that. So that's a bit different. So we have something, we have int a and int b, and then we have dash dash dash, and then int sum. All right, so this here, before the 3 dashes, this is the request that you're gonna send. And after the 3 dashes, this is the response that you're gonna get. So this node add to int server contains a server, so contains a service server named add to int. Now, in order to call this service, you need to send a request that is this one, int a, int b. And after you call the server is gonna process stuff, and it's gonna return a response which contains the sum. So let's actually try this. We can do ROS2 service. So we can call a service actually from the terminal. We can create a client from the terminal. So ROS2 service call, and then the service name, add to int, and then let's press tab twice. We need to provide the type. So ROS2 service call with the name, with the type, and then if I press tab again, well, you can see we have weird stuff, but what I can do is use actually curly brackets. So let's use curly brackets here, and let's put a like that. For example, is equal to 2, and then b with 5. Okay, so you can use curly brackets, and then the field a, you can put a with quotes, colon, the value you want. Here it's an integer, so I put 2, comma, and then do that for every field. I'm gonna press enter. So look what's gonna happen here. I press enter here, and actually, well, actually no, I need to do, so let's change this. Let's use double quotes around the curly brackets, and then single quotes inside. I think this is gonna work, and yes, this is working. So yes, if you want to call ROS2 service call from the terminal, make sure you use that syntax. And well, that's kind of tricky, even I forgot how it was working, but yeah, double quotes, curly brackets, and then fields with single quotes inside. So what's happening? You can see making requests with a is equal to 2 and b is equal to 5. That's what we want. And then the response with sum is equal to 7. Let's look at the server side. We have a log, incoming requests with 2 and 5. So the request was sent from the client here to the server. The server printed this log, incoming request, processed the request, and then returned a response with the sum. And you can see this happens almost instantly. Let's try again. Let's modify. Let's put 9. And you can see it's working too. We have sum 11, and here we will receive 2 and 9. All right, so you can see that a service is simply, well, a client-server communication. And for a service, you can have, well, only one server. Okay, the server is here in this node, but you can have many clients. Okay, I could call the service from this terminal. I could call it from another node, so I can have as many clients as I want. As an analogy, let's say you have a web server. So the web server for a specific URL, for example, we only have one. If you go to example.com, there is only one server on example.com. There is only one URL. But you can have as many clients as you want connecting to the server. Okay, so with a service, you have one server and as many clients as you want. And then we're gonna use services for mainly two kinds of requests. Either a computation, so that's what we did. We send some data in the request and we expect something in the response. That's a computation related to the request. And the second type of service is actually not a computation, but a change of settings. So in your robot, you may have a lot of settings, and you can use some services to be able to change the settings. So you will have a service server where you want to change the settings, and then other nodes can create some requests to change the setting. And actually, let's try that with the turtle sim. So I'm gonna just clear all of that. Let's kill this and clear. Let's run. So ROS2 run turtle sim node. Okay, I have the node here. Let's actually put this on the side. And let's do ROS2 service list. As you can see, we have quite a few services. So we have services that are related to the node turtle sim here, so we don't really worry about those. But then we have a bunch of services. For example, clear. So if you call clear, it's gonna clear all the traces, okay, that the pen has left on the window. Kill, you can actually kill a turtle, so you could remove this turtle. Reset, I think is gonna reset the turtle to the center. And then spawn, you could spawn another turtle, so you will have turtle 2, turtle 3, etc. And then, well, here the one we're gonna use is turtle1/setPen. Okay, so as you know, the trace that the turtle leaves is gonna be white or light gray, so that's what we call the pen. Okay, let's do ROS2 run turtle sim with turtle teleop key, and when I move, you can see, well, it's kind of light gray, all right? But we can change the color of this. We can change with setPen. So that's an example of how to change a setting. The service server is hosted on the turtle sim node, and then we can call this from another node or even from the terminal. So let's do ROS2 service type with setPen to know what we need to send. Okay, we need to send turtle sim service setPen. Now let's do ROS2 interface show with that. And what do we have here? Well, we have a request with RGB, so red, green, blue, and then the width of the pen and off if you want to turn off the pen. That's the request. Then we have dash, dash, dash. And you can see after dash, 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 we have nothing because, well, there is a response, but the response is gonna be empty. Okay, so it's possible that you create a service with an empty request or an empty response. No problem with that. So let's call this service to actually change the color. Okay, let's do ROS2 service call with turtle1/setPen with the turtle sim service setPen service, and then let's use double quotes, curly brackets, and then R will be, so here we need to give a number between 0 and 255. So let's say we want to change the color to red. I'm gonna do it simple. Let's do 255, and then G is gonna be 0, and then B is gonna be 0 as well. The width, so width, let's try, I don't know, let's try with 3, and off should be 0. Okay, let's press enter. You can see, so we have nothing on the logs of the turtle sim node. Why is that? Because simply, well, the server didn't print any log, but you can see it was working because we have the response. So we have an empty response because if you remember, well, in the interface, we don't have any response, so we still have one that is empty. And now let's try to move the turtle, and you can see now it's red. So the pen has changed to a red pen, and the width is 3. So I guess that the width was 3 before, so that's the same one. Let's actually change it. So let's send another request with 6, and then I don't know, let's put red to 0, green to 100, and blue to 100. Okay, and let's move the turtle again, and you can see now we have another trace. That's a bit thicker. And so here, well, as you can see, we have called the service from the terminal, and this is not that convenient if the service starts to be quite big. Okay, if the request actually starts to be quite big, this is not going to be convenient. But actually, of course, later on, we are not going to call the service from the terminal. That's just for debugging and testing. We are going to call it from the code directly. That's what we're going to see just later. And one more thing is that, so let's say I kill the turtle sim here. And, well, I don't need that as well. Let's try to call the service. And you can see waiting for service to become available. Okay, because the service, if I do ROS2 service list, well, the service is listed here because we are calling it. But let's do that again. We don't have any service. So if we try to call a service that doesn't exist, well, it is going to wait. Okay, maybe you will get an error, but here it's waiting. If I start the turtle sim, then you can see the service is going to be up, and then the request can be made. All right, so you have seen an overview of services through two different examples. And so you are going to use a service when you need a client-server kind of interaction. And when to use a service versus a topic, well, topics are going to be used to send some data streams. So if you need to send some data from one part to another part without expecting an answer, just sending some data, for example, sensor data, command velocity data, this kind of data stream will be handled by topics. But when you need to make some interaction where you're going to, for example, compute something or change a setting and you expect also an answer, then you are going to use services. So in this tutorial, we are going to create a service client with Python. And to see what we need to do, let's actually come back to the application with the turtle controller that we have. So let's run, so ROS2 run turtle sim with turtle sim node. Okay, we have the turtle here, and then we have the controller, ROS2 run turtle, no, actually my package, so my robot controller with turtle controller. So for now, what we have is the turtle is correctly controlled to move around and not hit the wall. What we want to do is we want to kind of split the screen in two and say that on the right, we want the color to be, let's say, red, and on the left, we want the color to be green. So the color of the pen, all right? So we wouldn't want to modify the color depending on if the turtle is on the right side or on the left side. And how can we do this? Well, ROS2 service list, we have just actually used, so this one, the turtle one set pen service. So we have just used this one in the previous tutorial to explain what are services. And so that's the one we are actually going to code. So we are going to code a service client inside our turtle controller so that we can modify the color of the pen depending on where the turtle is. Okay, so let's actually do that. I don't need to create any new node or anything. I can just go back to, so let's go to the source folder of the ROS2 workspace and let's do code dot, and let's go back to the code. So the turtle controller here, and so that's where I am going to create the service call. And where are we going to create the service call actually? Well, we are going to call the service from the pose callback. Okay, because we need to call the service depending on where the turtle is. If the turtle is on the right of the screen, which means that actually the pose x is greater than 5.5, which is the middle, then we're gonna choose the color red. If it's on the left side, we choose the color green. And so we will need to call the service, so to create a client with a request in the pose callback. Okay. And to do that, I'm going to create a new function, here, a new method in the class def call set pen service. Okay, because we will have a few lines of code to do that, so I'm going to create a method that is specific just to call the service. Okay, and let's do self, and then let's put all the parameters we need, so RGB width off. Okay, how do I know that? Because if you do ROS2 service type with the set pen. Okay, where do I have nothing? Okay, because, well, the service actually doesn't exist. I need to run ROS2 run turtle sim node. Then this should be better. And ROS2 interface show with that. We have RGB, width, and off. So those are the 5 parameters of the request. So I create a function and I just send this as the parameters. And then what do we need to do? Well, we need to create a client in the code. So client is equal to self. So self is the node, create client, as simple as that. What do we need to provide? We need to provide the service type. What is the service type? The service type is turtle sim srv set pen. So we are going to do from turtle sim dot srv. Okay, we did msg for messages for topic, and here for service we do srv. Import set pen. Now we need to make sure that we have the dependency to turtle sim, but we already added it before. Okay, in the package.xml we have turtle sim, so everything is good. So I have set pen that I can put here, set pen, and then we need to provide the service name. All right, so very similar as for topics. For topics, we need to provide the type and the name. Here we need to provide the type and the name. What is the name? The exact name is this, with quotes. It's gonna be better. Okay, and that's it for the creation of the client. So now we have a client, but well, actually we have nothing. We just have an object representing the client. What we will do is we will say, let's say we want to wait for the service. Okay, we don't want to call the service if the service is not up. Because if you call the service and the service is not up, well, you're gonna have an error. Here I'm gonna do while not client wait for service. So you have this wait for service method in the client here that you use with create client. And we need to provide a timeout, let's say 1 second. And here we're gonna do self.getLogger. We're gonna log something, and instead of info, I'm gonna use 1. Okay, 1 is gonna print something with the yellow color. And let's say waiting for service. So we do wait for service for 1 second if the service is up. So this is just gonna return immediately and we can continue. But if the service is not up, after 1 second, we're gonna print waiting for service, etc., etc., until the service is up. All right, now we have a client. We know the service is up. What we can do, we can create a request. So let's do request is equal to set pen dot request. So actually request with an uppercase and open close parenthesis. And then we are going to fill the request. So request dot r is equal to r. Okay, that's gonna be what we get from the parameter here. And then request dot g is equal to g. Request dot b is equal to b. Request dot width. All right. And the last one, request dot off is equal to off. So we just repeat the parameters inside the request. Nothing really fancy here. And then, well, we're gonna call the service. Okay, we have the client, the service is up, we have the request. Now we can call the service. So we can do client call async. So this will call the service in an asynchronous way. What does it mean? It means that it's gonna return immediately. If you call it just with the call like this, it's gonna call the service and then wait, so block right here until the service has replied. But if you do that, you may have some problems with the different threads, okay, with the spinning, and I'm not gonna go into much details here, but if you block the thread that's calling the service, you may have some errors, for example, that the response is never received. So I'm gonna call async, and I need to send a request. Okay, so client.callAsync request. This is actually going to give me a future object. Okay, so we are going to work with future. And also I'm not gonna go into much detail about future, but basically a future is something that's gonna be done in the future, basically. So you can work on this future, you can add a callback so that when you actually get the response from the service, then the future is gonna call this callback and you can process the request. And that's what we're gonna do. So I'm gonna add here a callback def callback. Let's call it callback setPen self, and also future here. So that's how to write the code. So here, well, I'm showing you how to write the code. It may sound a bit complicated for a service, but the thing is that it's always gonna be the same thing. So the first time you write the service client, it's a bit difficult, but then you're gonna write it a second time, a third time, and then you're gonna have written it 10 times, 20 times, and it's gonna be super easy at the end. So here in this function, let's do pass for now. And that's gonna be the callback for when the service replies with the response. Okay, we call the service, we send the request asynchronously so that this method is gonna return, and then we need to add a callback for that. And to add a callback for that, I'm gonna do future dot add done callback, and here I'm gonna use partial with self callback set pen. So I provide the callback here, and partial is not found. You need to import it. So from func tools import partial. That's one thing you need to import. Okay, with Python func tools and partial. Then we put future dot add done callback with partial self callback set pen, and this is gonna call this method when the service has replied. And in this, what we do is we do response is equal to future, so that's the future we get here, dot result. Also, I'm going to add this inside a try and except block, because we might have a service exception. I'm just gonna do except exception as E, and if I get an exception, I can do self.getLogger, and here I'm gonna use error. Okay, so that's yet another level of logs. Okay, we have info 1 and error, and I can say service call failed, and I'm gonna use this syntax with R here and then %E comma inside parentheses. So that's a specific syntax, but that's just how you can print an exception easily here with ROS2 services. All right, and now the service call is complete. So to recap quickly here, we create a client with self create client. We set the type and the name of the service. Then what you can do is you can also wait for service to make sure that the service is available. Then you create a request. You do client.callAsync to send the request to the server, and this is gonna give you a future object. Then you can add a callback with future.add done callback and partial. You can add a callback so that the callback is gonna call when the service replies. When the service replies, you need to do a try except block so that you can manage the exception if you get an exception. Okay, so if the service could not be correctly handled by ROS2, or if, I don't know, if anything bad happens, then you're gonna get an exception and you can print the exception with this syntax. And if everything works correctly, then by doing future.result, you're gonna get the response. And here, well, I do nothing with the response. Why is that? Because here with ROS2 interface show, you can see that we have this for the request, and then dash dash dash, and we have nothing in the response. So if you add something in the response, for example, with the add to int server that we have used previously, you could, for example, do response.sum, and that would be something you can use in this node class. Okay, you could use it to do whatever you want. You can process the response and do anything else you want. All right, so now we have the syntax for the service call. And this, well, basically this is gonna be almost the same every time you call a service inside a ROS2 Python node. Now, well, let's actually call this service because we have a method, but we don't use that method. Where are we gonna use it? Well, we're gonna use it in the pause callback. So what do we do in the pause callback? We get the pause, and then depending on the pause, we send a different command. We're not gonna change that. But after we do this, we're gonna also check where is the turtle. So depending on the X property of the pause, we're gonna change the color of the pen. So for example, if X is greater than 5.5, so actually pause.x. So we know that the middle point is 5.5. So everything on the right of the window will be more than 5.5. Everything on the left will be less than 5.5. So if it's more than 5.5, what we can do is to do self.call setPenService with, so we want it to be red. So let's do 255, 0, 0, and then width, let's put 3, and off, let's put 0. And then else self.call setPenService with 0. So 255 for the green, 0, 3, 0. All right, so right side of the screen, red, left side of the screen, green, as simple as that. And maybe we can also add a log, self.get logger dot info, set color to red. And let's do the same here, self.get logger dot info, set color to green. All right, so we know when we send the request actually. If you want, you could also add some logs in the call setPenService and also in the callback, so in the try block, to see when you get the response, when you send the request, etc. Good, so this should work, but I'm gonna add something else because, well, now the question is how frequently this is going to happen. For now, we didn't really worry about that, but now we should. Why is that? Because, well, when you publish on a topic, you can publish at very high frequencies. For example, 100 Hertz, 1000 Hertz, that could work also. Even a few thousand Hertz, sometimes you have some topics that are published very, very frequently. But for services, a service is not made to be called 100 times per second, okay? A service is made so that it's called when you need to call it, in a punctual way. So it doesn't necessarily mean that you can't call a service 10 times per second, but the best way to handle services is just to call them when you need to. Otherwise, it can really slow down the application. So let's find out. So what do we need to find out? We need to find out how frequently we get the pause. And this we can use with another command. So we have, so turtle sim is running here, ROS2 topic list. We have the pause. How frequently do we receive a pause? Well, that's a good question, and we can get this with ROS2 topic HZ, okay, for Hertz. That's gonna give us the frequency of the topic. Let's do this, and it's gonna listen to the topic. So let's wait a bit and let's do Ctrl+C. It's gonna listen to the topic and then publish the average rate, which gives you an idea of how frequently you get some messages on that topic. And you can see we have about 60 messages per second, so 60 Hertz, which means that this callback is called 60 times per second. We publish a command 60 times per second, and with this code, we would call the service 60 times per second. So for a publisher, 60 Hertz is good. For a service, you don't want to call a service 60 times per second. So what can we do to solve that? Well, it's quite simple. We can, so let's use the turtle here. We can keep track of the X position, and we can actually just change the color when the turtle crosses the middle, okay? So when the turtle goes from left to right, or when the turtle goes from right to left. We don't need to change it when the turtle is left, and that stays left, okay? the color is going to be the same. Okay, we need to change it when the turtle crosses the middle. So we have two cases here. When the X position is lower than 5.5 and then the X position is greater than 5.5, or when the X position is greater than 5.5 and then the X position goes to lower than 5.5. So let's create, well, let's do that quite quickly, but let's create here self previous X, and let's just put 0 as an initialization value. Okay, and we're gonna do if. So if the pose is greater than 5.5 and self previous X is lower or equal than 5.5. Okay, so it means that before the turtle was on the left and now the turtle is on the right. Then we change to red. And then else, I'm gonna add else if actually. So not else if, but elif with Python. Pose is lower than 5.5. Actually, let's use lower or equal here. And self.previous X greater strictly than 5.5. So this means that it was previously on the right side and now it is on the left side, and then we want to change the color to green. And of course, we need to do self.previous X is equal to pose.x. Here and also here. Self.previous X is equal to pose.x. So that's a very quick way to solve this issue. Maybe there are different logical ways to do that, but this is quick and easy, and that's gonna be enough for this tutorial. So we initialize the previous X to 0, doesn't really matter. And then when we go from left to right, we set the color to red. We also save the previous X, and we do the same when we go to the other side. So that if we stay on the same side of the screen, okay, so if we stay on the left, we are not going to call the service. If we stay on the right, we are not going to call the service, only when we cross the middle. Okay, I'm gonna save this, and this should be it. So actually, let's find out and let's try. That's the only way to know. Let's kill everything here. Clear. Let's do source -rc because I'm gonna run the script from there. I'm gonna run the controller from there. Here, let's do ROS2 run turtle sim with turtle sim node. Okay. Here we don't need that screen. And let's run, so ROS2 run my robot controller with turtle controller. Let's see what happens. Okay, and we have an error, which is this is not supported between instances of pose and float. Let's find out with the code. Yes, actually it's pose.x. I forgot the .x. So of course I can't compare a pose with a number because that's something that's different. Let's try again. So let's run this and let's try this again with source-rc and run the controller. Okay, you can see it's red and then it crosses the line and it's green, and we have a log too. It crosses the line and it's red, and you can see set color to red and then set color to green. All right, and then again and again. I'm gonna leave it just a bit so you can see what's gonna happen at the end. Okay, great, you can see it's working quite well. The turtle continues to move, tries to avoid hitting the wall, and whenever it crosses the middle line, it changes color. So you can see everything on the right is red, everything on the left is green. So everything is working as expected. And well, congratulations, you have just written a service client with Python. You have also mixed it with some publishers and some subscribers in just one node. So you have already a complete ROS2 application. Hey, it's Edward. I hope you enjoyed this crash course and that you found it useful. Now, if you want to continue to learn ROS2 with a full and in-depth course covering everything about the ROS concepts, Python and C++ code, and also more practice activities, well, I have the course just for you. This ROS2 course contains more than 10 hours of structured video content and also downloadable code for each activity and project. You will dive into the ROS concepts with much more details and also discover ROS parameters, launch files, how to write service servers, and many other things. So if you like the way I teach, check the course out. The link is in the description. Click on the link, read the course description, and decide if you want to continue. Alright, thank you for watching, and I hope to see you in the course.